All right, so for the last, well, let's go back. Huh? For the last problem I want to see is I want to show you one where there's friction, and why this comes up again. We don't live in a perfect world, and in all reality, when we solve any problem and look at things in real life, we have to think about friction. Now remember, friction is non-conservative work, so therefore that's going to release energy. Usually it's thermal energy, and that's what we're going to talk about here is the thermal energy. Okay, so here's an example of what this looks like. So we have a roller coaster from the previous problem up at 40 meters. There's at the very bottom, there's its height, and then here it is at 25 meters. Okay, so the car releases as it goes down. It gets to the bottom. As it comes back up, it stops. So friction has caused it not to make it to the top of this hill, which means if you want to make a roller coaster do this, you're going to have to find a way to reduce friction so you don't have to add more energy to the whole process. But we want to determine the thermal energy produced and the average force of friction on the car, whose mass is 1,000 kilograms. Okay? So this is how we can do this very quickly and very painlessly using energy. So let's talk about our situation. We're at here and we're going to here. We don't have to talk about the bottom, what's going on at the bottom. We just need to understand that that is our 0 point. Okay? So let's talk about initial. Here's what we got initially. Initially, we have an opportunity for potential energy and kinetic energy. Okay. Here in the middle, or at the end, there's going to be potential, and there's also going to be kinetic. Now, the other thing I'm going to add to this is not the non-conservative forces or work. Okay, and we're going to call it thermal work. That's going on here. You call it frictional work. I'm going to call it thermal because that's what they're looking for, is thermal energy. So here's where we're at, all right? In fact, I'll call it friction too. So whatever you want to call it. But work due to friction, okay? So I look at this. At the very top, I have potential. I start from rest. There's no kinetic. Now let's look here. When we get to here, potential, yes, okay? But do we have kinetic? At the very top, it says it goes to a stop, which means no kinetic at the top either. But what we lose in potential goes off as work. So the potential we start with will equal the potential we finish with plus the work that happens due to friction. Okay. So let's start substituting numbers in. Potential mgh. Again, we don't. Do we have a mass? We have a mass of 1,000 kilograms. Okay. G is 9.8. And our height at that point is 40. Now we look at final potential. 1,000 times 9.8 times 40. And from this, we can find out how much work we have lost to friction, right? I mean, that's as much as multiplying and subtracting, multiplying all this, and subtracting this from this. And we can find our work. Okay? So the thing about work is, and if you remember the definition of work, it's force times distance. So with it being force times distance, I can substitute force times distance here. All right? Why that's important is because right here, we know the distance traveled is 400. So the frictional force times 400 can go into here. All right? So let me write the whole thing out again. We got 1,000 times 9.8 times 40 equals 1,000 times 9.8 times 25 plus our force of friction times 400. So now I can do the math we just talked about. Multiply this, subtract this from this. We'll equal that, and we just take that whole answer at the end and divide by 400. And we can find our force of friction approximately, all right, approximately to be 300 170 newtons. Now, never perfect, but just think about the work that we just did that before took so much time when we talk about kinematics. And energy, again, can escape some kinematics problems. So as you're solving problems, before you automatically go to kinematics when we're talking about velocities, be sure, or friction for that matter, be sure to look at energy also. And this is the last problem for energy to show you.